All right, now let's talk about our 30, 60, 90 triangle, right? 30 plus 60 plus 90 equals 180. It's a very special triangle when we talk about trigonometry. All right, so I've labeled this side DFR. That's one of the legs of this right triangle. I don't know the hypotenuse, and I actually don't know the other leg because it's not an isosceles triangle, so I can't just assume that the leg's the same. So what I'm going to do is a little bit of construction. I'm not going to do it formally, but basically what I'm going to do is I'm going to reflect this triangle over EF. I'm going to take it and flip it over EF. You'll see why that's helpful in a second. Obviously this is not a beautiful diagram, but it's pretty close. Okay. So because I flipped it over, right? Since I reflected it, let me use the proper math vocabulary, Mr. Benak. Since I reflected it, it's a rigid motion, so this triangle is going to be congruent to this triangle. So what that tells me is that, this angle is 60, this angle is 30, this angle is 90, and then I know that this is also going to be R. So what that tells me is that if both of these are R, and this whole side is going to be 2R. 2R is opposite from this angle up top, which is 30 and 30 combined, aka 60. So if you notice, what I did when you reflect a 30, 60, 90 triangle over the long leg, it becomes an equilateral triangle. So what is true about an equilateral triangle besides the fact that I've got 60, 60, and 60? Well, I also have every single side being equal. So if this is 2R, that means that this hypotenuse over here is also 2R. Let's call that the hypotenuse because it's opposite from my right angle. All right, so now I've got two sides of a right triangle. I can use the Pythagorean theorem to find this last leg, EF. So a squared plus b squared equals c squared. One of my legs is r, so I'm just going to write r squared. The other leg is EF, so I'm going to write EF squared. And then lastly, I've got c squared, or 2r squared. Very important you put parentheses here because many students are going to make a mistake on this next line, I guarantee it. All right, so here we've got, let's just simplify first, r squared plus EF squared. And I guarantee you most students will write, not most, but many will write 2r squared. If I wrote 2r squared where only the r was squared, I'd have forgot to square that too. Really what this means is 2r times 2r. So 2 times 2 is 4, and r times r is r squared. All right, the next thing I'm going to do is try and get EF alone. So subtract r squared from both sides, and we're going to get EF squared is equal to 3r squared. Same thing we did last time. I'm going to throw a radical of both sides. And I'm going to get that EF is equal to radical 3 times r. Because really this is just equal to radical 3 times radical r squared. And r squared, when I radical it, is just r. So this side here is going to be radical 3 times r. All right, so that's always the case in a 30, 60, 90 triangle. If you know the side opposite 30, you double it to get the hypotenuse and multiply it by radical 3 to get the leg opposite 60 degrees. So let's relate this back to our trig table now. So now I want to find sine of 30, cosine of 30, tangent of 30. So let's do that. I need a little more room. Okay. All right, so let's start out with sine of 30. That's equal to opposite over hypotenuse. So if I'm, well, actually, I should really shouldn't write sine of theta. I should write sine of sine of 30, so I know what angle I'm talking about. This is why it's a little bit trickier than the 45, 45, 90, because it didn't matter which my reference angle was. Now it actually does matter quite a bit. All right, so let's take a look here. Opposite of 30 degrees will be R, so that's opposite. Hypotenuse is 2R, that's always the case. And then adjacent will be this side, radical 3R. All right, so sine of 30 will be equal to opposite over hypotenuse. Opposite in this case is R. Hypotenuse is 2R. And we can simplify this. R and R will cancel out. And I'm just left with 1 over 2. R divided by R is 1. Anything divided by itself is 1, right? All right, so that's very nice. That's the first nice and clean fraction we've got. Been dealing with a lot of radicals, so it's a welcome sign to see this. All right, so that just, all this means is that sine of 30 is equal to 1/2. If sine of 30 is equal to 1/2, which cosine value must also be equal to 1/2? Well, what angle is complementary to 30? 60 is complementary to 30, so that means that cosine of 60 must also be 1/2. That's why it's nice dealing with complements. I can also show that later. We will show that later, but I can just fill that in right away. It's always good to see the shortcuts. Next, we've got cosine of 30. So that's adjacent over hypotenuse. Adjacent would be radical 3 times R. And hypotenuse would be 2 times R. Again, cancel out my R's, and I'm just left with radical 3 over 2. So that'll be cosine of 30, radical 3 over 2. Obviously, not a dream to be working with radicals, but it is always going to be this value, and you will see this radical 3 over 2 pop up a lot. You'll see radical 2 over 2 pop up a lot, so it's good to know what they are talking about. All right, next we have tangent. So I could, well, actually I will, because I think it's good to see it, how to do it with trigonometry. Tan of 30 is opposite over adjacent. That's equal to, opposite is R, adjacent is radical 3 over R. That radical 3 times R. So again, I've got a nice situation where these are going to cancel out, and I'm just left with 1 over radical 3. I don't like having radicals in my denominator, so I multiply both sides by radical 3. I multiply this by radical 3 over 3. It's just the same as 1. These will cancel out, top and bottom. I don't know why I did that. I'm sorry. You'll see what I was stupid. Because now I'm just left with 1 over radical 3 again, right where I started. So don't do that. Do this way. Do 1 times radical 3. It's just radical 3. And radical 3 times radical 3 is 3. Or radical 9, which is equal to 3. So this is a much cleaner fraction. I've had math teachers who say they don't mind radicals in the denominator. Personally, I've always been taught not to do it by, my math teachers who I really respected a lot. So I would recommend doing that. All right, so we got radical 3 over 2. I'm sorry, radical 3 over 3. We can also show that by dividing sine of 30 by cosine of 30. That will tan of 30 will always be equal to sine of 30 over cosine of 30. Always. All right, so sine is 1 over 2. Cosine is radical 3 over 2. Keep, change, flip. All right, so I'm left with 2 over 2 times rad 3. 2's cancel out. You can see we're headed in the exact same direction we were before, where we had 1 over radical 3. So using that same method of getting that radical out of the denominator, I'm left with radical 3. over 3. Okay, so knowing what we talked about before with sine and cosine sometimes having the same value, right? These two are both 1/2 because one's 30, one's 60. Those are complementary angles. So knowing that, what will sine of 60 have to be equal to? Well, sine of 60 will always be equal to cosine of 30. So this is going to be radical 3 over 2 as well. All right, the tangent, however, will be a little bit different. Let's investigate that a little bit. Okay, so tan of 60. So now we've got 60 as a reference angle. So here's my 60 degrees. Now this is going to be the opposite side. Remember, we've switched our reference angle to 60. So that's going to change things up a little bit. So now I've got opposite, adjacent, hypotenuse stays the same. That's not going to change at all. The hypotenuse is always the hypotenuse. All right, so now we've got opposite over adjacent. That's equal to radical 3 times r over r is adjacent. That's just going to be equal to radical 3. Quite simply, radical 3. All right. So now we get tan of 60 is radical 3. Okay. I will say that the tangent ones are really the least important ones to remember, because if you know sine and cosine, what I was trying to show you before, anytime I know sine and cosine, I can just divide sine by cosine to get the tangent. You will see these a lot, but the earlier you see them, the better. It's better when you show up to Algebra 2 to sort of have an idea of these rules, because you know how to do this on the calculator. You can plug sine of 60 in no problem, but it's not going to be a fraction. It's going to be a irrational number. Let me demonstrate that on the calculator. All right. So let's say I'm looking at this column. Sine of 30 is going to be fine, right? Sine of 30. It's 0.5. That's 1/2. Same thing. All right, 1/2. That I would have no problem writing out. This one, though, is not going to be fun. Cosine of 30. Yikes. And we can check that our work is correct. We can just write radical 3 over 2. We get the exact same answer. Another thing that actually I just realized we should be doing, you can go to mode now and go to radian mode. I could do sine of pi over 6. Let's get the same thing. Let's try cosine of pi over 6. Good. Tangent of pi over 6. So I can do all this stuff on radian now. All right, let's see if that's actually the same as radical 3 over 3. I know it is, but just to show you, seeing is believing sometimes. And we get the same exact thing as what we got before. All right, so obviously, some of this stuff you can do on your calculator, but if they tell you they want an exact answer, exact means no decimals. You're gonna want to know these rules. They're very, very important for that. All right, so that's all we got for the special right triangles. Yeah, that's it for now. We will work on how to find 0 and 90 tomorrow. All right, have a good one.